So in this video I am going to prove an important theorem, a special case of an important theorem called Cauchy's theorem. Okay, so this is a good application of the concept of quotient groups. So this is useful to you will understand in this proof why it's useful to look at quotient groups. So Cauchy's theorem says that, so this is the following. So let G be a finite abelian group. Okay, so it's a finite group, so meaning it has only finitely many elements, and it's an abelian group, meaning any two elements in G commute with each other. Suppose that a prime number P divides the order of G. So P is a prime number that divides the order of G. Then G has an element of order P. Okay, so then G has an element of order P. So this is Cauchy's theorem. We will first prove this and then look at why this is a surprising statement. If G has an element of order P, it's a strong condition on the group. So, and it's important to note that P must be a prime number. So all this we will see after we prove the theorem and see where we use the prime number hypothesis. So again, let's just see the statement. G has an element of order P. What is the element of an order? An element of order of an element. Recall, order of an element A is the least positive integer D such that A power D is identity. So there is such an element in the group G. So we are going to consider the size of the group. So we will prove this in two cases. We will consider two cases. Okay, so the cases are the following. Case 1, G does not contain a subgroup H such that 1 is strictly less than order of H, which is strictly less than order of G. So remember, G is a finite group, so I can talk of order of G is the number of elements. So suppose G does not contain a subgroup H which has this property. That means cardinality of H is strictly greater than 1 means H contains elements that are different from identity element, and order of H less than order of G means H is a proper subgroup. What if G does not contain such an element? So then I will first solve this problem prove the theorem in this case. So choose an element A in G such that A is different from E. E is the identity element. Why is there an element A such that A is different from E? Such an element exists because cardinality of G is greater than 1, right? Why is cardinality of G greater than 1? Because I am assuming that a prime number P divides the order of G. So if cardinality or order of G is 1, certainly no prime number divides it. Prime numbers are 2, 3, 5, 7 and so on. So order of G is at least 2. That means there is an element A which is different from E. Consider the subgroup generated by A. Now what are we considering in this case? In this case we are assuming that G does not contain a subgroup H which is non-trivial and proper. Okay, because A is different from E, by hypothesis A is different from E by choice, so the subgroup generated by A cannot be identity and hence it has to be all of G, right, because G does not contain any subgroup that is non-trivial and proper. A is the subgroup generated by A is non-trivial because A is different from E, so it must not be proper, so it is equal to G. On the other hand, so in particular G is a cyclic group, right. What is the order of note that if you have a cyclic group generated by A, order of G is equal to order of A, because this is because G is nothing but E A squared A power order of A minus 1, right. You take powers of A and go all the way up to order of A minus 1. The next power, which is A power order of A, will be E. So this is G. How many elements are here? Order of A, many elements are there. So that's the order of G. So this is okay. Now, and what are we assuming? We are assuming that P, we assumed, we know P divides order of P divides order of G, which is order of A. Okay, so now we have to exhibit an element of order P. So if P divides order of A, I'm going to okay, so the best way to complete now is to through the following exercise. So which I will leave it as a separate exercise and I will do this later in a different video or maybe in the same video, but it will interfere with the proof of Cauchy's theorem, so I don't want to spend time on this. If G is a cyclic group of order n and M divides n, okay, so then G contains an element of order. Okay, so this is not a difficult exercise at all, and this is a very general, so n, m are positive integers. And it has nothing to do with primeness. So if G is a cyclic group of order n and m is another number that divides n, then G contains an element of order m. So this is sort of a converse to Lagrange's theorem, which I proved earlier. What is Lagrange's theorem? It says that if G is a finite group and you have an element, its order divides the order of the group. I am saying now that if I am further assuming G is cyclic and an number divides its order of the group, then there is an element of that order. Now by the exercise, G contains an element of order P. because G is cyclic, that is what we have concluded. G is a cyclic group. So and P divides the order of the group. So G has this element of order P. So if the group is assumed to be cyclic, very strong statement is known, much stronger than Cauchy's theorem. Cauchy's theorem says that if P is a prime number and P divides the order of the group and G is abelian, that is a version of Cauchy's theorem we are doing now, then there is an element of order P. But the exercise is saying that if G is cyclic, the life is much simpler. For any M dividing the order of the group, there is an element of that order. So I will do this exercise later, but we are done assuming the exercise. So now let's go to case 2. Okay, so in case 2, what is the complement of case 1? Case 1 was there is no subgroup of G which is non-trivial and proper. So case 2 would be there is a subgroup of G which is non-trivial and proper. So there is a subgroup H of G which is non-trivial, that is H is different from just the trivial group, and proper, that is H is different from G also. So we have one strictly less than order of H, strictly less than order of G. Okay, now I am going to use induction. Use induction on G. So what does the theorem say? Theorem says that if G is an abelian group of a finite abelian group and a prime number divides its order, then G contains an element of that order. So what would be the base case of S? Base case of for induction, because I want to take an order which is divisible by a prime number. So let's take order of G is 2. In this case, we have seen this numerous times. G is A and E, and order of G is divisible by 2 and order of small a is 2. So the only prime that divides the order of G is 2 and there is an element of order 2. So this is okay. Base case is proved. Right? Now I can assume that up to some number all groups of that order which are abelian, and if a prime number divides them, there is an element of order P. So now we know that order of H is order of G, strictly less than order of G. So suppose that P divides order of H. This is not necessarily true, but suppose it's true. P divides order of H. We only assume that P divides order of G. Suppose that P divides order of H. Then by induction, because order of H is strictly less than order of G, and we are looking at the order of, so induction hypothesis is that anything which has order less than order of G, the theorem holds. Now H is an abelian group, right? G is abelian, that implies H is abelian. Abelianness is inherited by subgroups. Any two elements of G commute with each other. So certainly any two elements of H also commute with each other. So H is abelian, its order is less than order of G, and P divides order of H. So by induction, H contains an element of order P. Right? This is the induction statement. But if H contains an element of order P, then so does G. That is immediate, right? If H contains an element small a of order P, A belongs to H, order of A is P, implies A belongs to G. H is a subgroup of G, and order does not change. Order of A is order of A. So G contains an order of G contains an element of order P. So this is the easy case. If H is P divides order of H, then we are done. So suppose that P does not divide order of H. This can happen, right? P divides order of H or P does not divide order of H. But now recall counting formula that we learned while proving Lagrange's theorem. It says that order of G is equal to the order of H times the index, right? Now since we have assumed that G is abelian, every subgroup is normal, right? In an abelian group, G mod H is a group, and note that order of G mod H is the index of H in G. Now if you look carefully at the counting formula, you have order of G is equal to order of H times order of G mod H. Right? And what is hypothesis? Hypothesis is that P divides order of G. P divides order of G, and hence P divides order of H times order of G mod H. And a property of prime number says that P divides order of G mod H. See, P divides order of G, P does not divide order of H, so P divides order of G mod H. This is a property of prime numbers. If P is a prime number and it divides a product of two numbers, it must divide one of them, and it does not divide H is our hypothesis. So P divides order of G mod H. And note that order of G mod H is equal to order of G mod order of H, which is less than order of G also, because H is a non-trivial group. This is because order of G is order of H is greater than 1. So induction hypothesis okay. So in order to make sure that induction hypothesis applies to G mod H, we need to check that G mod H is an abelian group. Is that clear? If G is abelian, G mod H is abelian. This is a very easy exercise that anyway I will later do in a video. G mod H is abelian, order of G mod H is less than order of G, and P divides order of G mod H. That's what I noted here. So induction hypothesis applies to G mod H. So I want to emphasize a very important point here, that I need to assume that G is abelian here. Okay, and that's why I stated in the original theorem itself that G is abelian. Because if G is abelian only, you can consider G mod H for an arbitrary subgroup H. Otherwise, G mod H is not a group, it is just a set of cosets. So now what does the hypothesis say? Induction hypothesis. So by the induction hypothesis, G mod H contains an element of order P, right? Because G mod H is an abelian group, its order is divisible by P and its order is less than order of G. So it contains an element of order P. But what are elements of G mod P? They are left cosets of H in G. So say GH in G mod H has order P, right? This means GH power P is equal to H, because that is the meaning of order. I mean GH power PH is H and GH is not equal to H, right? If order of GH equal to p implies this. P is the smallest positive number such that GH power p is identity, which is h. In G mod h, identity is h. So GH power 1, because remember p is strictly more than 1 always. P is a prime number. So GH cannot be h and GH power p is h. But what is GH power p? That means G power ph is h, right? And of course GH is not in h, not equal to h. That means G power p is in h and G is not in h. This is the meaning when you pull the element back to G. G is an element of course G is an element of capital G. Its power, its pth power is in h and itself it is not in h. Okay, so G power p is in h, G is not in h. Now let us denote by m the order of h. Okay, so I'm just giving it a name. Let m be the order of h. Then what we have is by Lagrange's theorem, applied to h, what is Lagrange's theorem? It says that if you have a group and an element in it, finite group and an element in it, order of the group, order of the element divides the order of the group. Order of G power p divides order of h, which I called it m. Okay, but if order of G power p divides m, and this is something that I have seen, I have shown before, G power p whole power m is equal to e. So this is the exercise that this came up in several places. If G is an element of a group G and order of G is, let's say, A, and then G power A n is E for all n, right? So if here m is divisible by order of G power p, so m is order of G power p times something. So G power p times m, power m is identity. This means we have G power pm is identity. So I have also remarked numerous times that usual exponent rules apply to taking powers of elements in a group. So this is, remember, I can always switch the exponent. So G power p whole power m is identity means G power m whole power m p is identity. So now can we say that order of G power m is p? Can we say this? See, not quite, right? Because what is order of G power m? This is the least positive integer such that G power m power p is identity. We have certainly G power d, least positive integer d, such that G power m power d is identity. We know that G power m power p is identity, but what if there is a smaller number? So what we can certainly say is that since G power m power p is identity, we can say that order of G power m divides. Okay, so this is also an exercise. This is sort of the converse to this exercise that I wrote in the box here, that also we have repeatedly discussed. If you have an element, its order is 3, only way that a power will be equal to identity is if you take multiples of 3, right? So recall, if order of G is A and G power n is identity, then A divides n. Using this, we conclude that order of G power m divides P, because G power m power P is identity. So order of G power m must divide P, right? This is discussed in various previous videos. So hopefully you'll remember. Otherwise, go back and see some of the videos that talk about this. But now P is a prime number, so we're going to use this fact now. And I think this is the first time we are using that P is a prime number, right? P is a prime number. So actually it's not the first time. We have also used it here to say that if P does not divide order of H, if P does not divide order of H, P divides order of G mod H. That also, here also we have to use it. So P is a prime number, so only numbers that divide P are 1 and P. So order of G power m is 1 or order of G power m is P. Right, I have observed here that order of G power m divides P, but P is a prime number. So order of G power m is 1 or order of G power m is P, because only numbers that divide P are 1 and P. But order of G power m is 1 means what? G power m is identity. Right, an element has order 1 if and only if it is identity. But if G power m is identity, that means if G power m is identity, apply Lagrange's theorem. So now I'll do so G power m is identity, let's say. So I want to say that this is not possible. Why? Why? The reason is, this is not possible because G power m is identity, right? Suppose G power m is identity. This implies order of G, okay, so if order of G power m, which we know is either 1 or P, if order of G power m is 1, then G power m is E, which I claim is not possible. So why is that? If G power m is E, then certainly GH power m is GMH, which is EH, which is H. So G power H, GH power m is H. But recall, how did we pick up GH? Order of GH is P, right? That is the way we constructed, we chose, because by induction hypothesis applied to G mod H, it contains an element of order P, so GH was that element. So GH power m equal to identity and order of GH is equal to P, that means P divides m. By the same exercise as before. If order of G is A and G power n is E, then A divides n. But P divides m, this is not a good thing, right? Because then P divides, what was m? M was the order of H. So we simply called m the order of H. Somewhere I wrote that, right? We let m be order of H. So, but we are assuming that P does not divide order of H, because if P divides order of H, we would not even do all this. If P divides order of H, we are done right away. So P does not divide order of H is our assumption, and now we are getting that P divides order of H. So G power m cannot be equal to E, so this is not possible. So order of G power m is P, and we are done, because remember we want to exhibit is the element we are looking for. G power m is the element we are looking for. We want to exhibit this completes the theorem, proof of the theorem. We want to exhibit an element of order p. Just to recap, so this is you have to carefully follow the proof that I gave. I'm going to spend 2 minutes recalling the proof, how we did this. The Cauchy's theorem says that if G is a finite abelian group and P is a prime number that divides the order of G, then G has an element of order P. The first case, which is easy, is that G has no non-trivial proper subgroups. Then we conclude immediately that G is cyclic, and by this exercise, which I will do later, we are done. So the interesting case is there is a subgroup H of G which is non-trivial and proper. Then using abelianness of G, we have that H is normal, which we will use later. So we know that order of H is greater than 1 and less than order of G, and we use induction. So if P divides order of H, so by the counting formula, P must divide either order of H or order of G mod H, because P divides order of G and P is a prime number. If P divides order of H, immediately by induction, H contains an order P element, so G also contains an order P element, the same element. Otherwise, G mod H contains an order P element, let's call that GH. Then we played with that element and concluded that an element that is related to it is the element that we are looking for. Okay, so the last part of the proof is somewhat tricky perhaps, so you have to carefully read the proof and listen to my proof once more if needed to make sure that you understand. Okay, so this completes the proof of Cauchy's theorem.